Okay, thank you everybody for being here and for coming to pitch and for having me. And so the topic of my talk, the broad topic of it is called generalized descriptive set theory. So I'm just going to say a few words about what that even is. So classical descriptive set theory studies the subsets of reals which are definable in some sense, and definable subsets of other Polish spaces, i.e. countably based, completely metrizable topological spaces. And for the purposes of this talk, you can just think of the Baire space of functions from omega to omega, so functions from natural numbers to natural numbers. I use omega to denote natural numbers with the product topology. So it's generated by functions with finite support. And so what do I mean by definable subsets? For example, Borel subsets, which is just the sigma algebra generated by the family of open subsets. So that means just close the family of open subsets under taking countable intersections and unions and complementation. Analytic sets, which are the continuous images of Borel sets or equivalently of the whole Baire space. And projective sets, which are just generated from Borel sets by closing under continuous images and complements. So it studies certain properties for these sets. And what generalized descriptive set theory does is it replaces omega, so the set of natural numbers, by some uncountable cardinal kappa with this, this property, which I'll say a bit more about later. So replace omega by kappa everywhere where it makes sense and see what happens. For example, the generalized Baire space is the set of functions from kappa to kappa equipped with the bounded topology. So instead of functions with finite support, you take functions with support less than kappa. And this is where this cardinality assumption comes in. So capital less than kappa holds by definition if and only if for all alpha less than kappa, the set of functions from alpha to kappa has size at most kappa. And so the bounded topology is equivalent to the topology generated by functions with support less than kappa. And the generalized Cantor space is just 2 to the kappa with the subspace topology. And, this assumption capital less than kappa holds if and only if 2 to less than kappa equals kappa. So the power set of a set of size less than kappa has size at most kappa, and kappa is regular. And sometimes, like it's very recently, people are looking at what happens when this assumption of regularity is dropped. But we're sticking to this this more classical case. And in this case, so instead of Borel sets, I take kappa Borel sets. So just take the kappa plus algebra generated by family of open sets. So instead of countable unions and intersections, I'm taking unions and intersections of size kappa and complementation. Kappa analytic sets are the continuous images of kappa Borel sets, and kappa projective sets are generated by closing under continuous images and complements. So kappa analytic sets can be equivalently characterized as the continuous images of closed sets, but not of the whole Baire space kappa to kappa. And in general, when we replace omega by some uncountable cardinal kappa, the structure of these spaces can look very, very different from the classical case. Some results, such as the one on the slide, fail outright. And most of the times, what happens is that a result that we care about, which holds in the classical case, is independent in the uncountable case. So by independent, I mean that there is a model of ZFC where it holds, and there's another model where it fails. So the structure of these generalized Baire spaces depends on which model of ZFC, so which model of set theory we are in. And what one main area of classical descriptive set theory is the study of regularity properties and dichotomies for definable subsets spaces. And so we're looking at dichotomies for subsets of generalized Baire spaces. So by a dichotomy, I mean some statement which says that a given set, a given definable set is small in some prescribed sense. It's either small or it contains a copy of a large canonical object. So any statement of that form is a dichotomy. And one of the simplest ones is the kappa perfect set property. So in this talk, I'm always going to assume from now on that kappa is an infinite cardinal with this cardinality assumption. So it's either omega or some uncountable cardinal kappa as before, and that X is a subset of the kappa-Baire space. And so the perfect set property for X says that either X has size at most kappa, or there is a continuous injection from the kappa Cantor space into X, or equivalently, X contains a homeomorphic, close homeomorphic copy of the kappa Cantor space. For kappa equals omega, this is equivalent to the classical perfect set property, where we're looking for a perfect subset of X in the sense that it's closed and has no isolated points. And so in the classical case, the PSP holds for all analytic subsets of the Baire space. This is just an FC theorem, but the situation is very different in the uncountable case. So it's consistent that the kappa perfect set property fails for all closed sets at all uncountable regular cardinals, and in particular, this holds in the constructible universe L. And for uncountable cardinals, the kappa perfect set property is actually consistent with the existence of an inaccessible cardinal above lambda. So what I mean is that there exists a model of ZFC where the kappa perfect set property holds for closed sets if and only if there exists a model of ZFC with an inaccessible cardinal above kappa. So an inaccessible cardinal, it's just a cardinal which so there are such things as large cardinals, which are cardinals which satisfy some assumptions, which is independent of ZSC. And the existence of an inaccessible cardinal is in some sense the weakest large cardinal assumption. And in particular, so we already know that it's possible for the kappa perfect set property to fail for closed sets in V equals L. But if we take a different model of ZFC, which is constructed starting out from an inaccessible above kappa, then we can get a model such that the kappa perfect set property holds for all kappa projective sets. So not only for closed sets, but this and even broader class and projective sets. I'll get to this in a later slide. And many dichotomies in classical descriptive set theory can be characterized via games of countable length. And in generalized descriptive set theory, we look at games of length kappa, and we look at how or whether these characterize some regularity properties. So, so what do I mean by a game? I just mean that there's a set A which denotes the moves of the game that the two players can play. So there are two players, 1 and 2, and they always play some element of a set A. And there's a subset X, which is a subset of the sequences of length kappa, which will be generated at the end of the game, and it's going to specify the winning conditions. So it's going to tell you when one of the player wins. So more specifically, there are two players, 1 and 2. They always play some element AI of the set A in each round I. And at the end of the end of all kappa rounds, I get a sequence of length kappa. So this is an element of the space A to kappa. And I say that 1 wins this instance of the game if this sequence A is an X, and 2 wins otherwise. And I'm going to say that such a game is determined if one of the players has a winning strategy. So a winning strategy is just some function which tells you, for example, it tells player 1 what to play at every step, at every round of the game, depending on the previous moves of player 2. And if such a strategy exists for either player 1 or player 2, then I say that the game is determined. Okay. So assuming the axiom of choice, in the classical case, all games where the winning condition X is Borel, all such games are determined. So this is a famous result of Martin with a highly non-trivial proof. And under the axiom of choice, it's easy to construct a pathological set or pathological sets in general, and it's easy to construct one where this game is not determined. And using this fact, in the uncountable case, one can construct a open, so closed and open set, like the simplest kind of set you can imagine. So you can construct a open set of A to the kappa such that these games are not determined. So you don't really have determinacy in general. So the general aim of this talk is to find a general class of games such that these games are determined for definable sets. And we get interesting dichotomies we care about as special cases. For example, the perfect set property or some other ones I'm going to mention on the slides. So before I get to the general class of games I'm going to consider, I want to talk about a game of length kappa characterizing the kappa perfect set property. So here, the moves for player one are sequences of 2 to less than kappa. So they're sequences of zeros and ones of length less than kappa. And player two is allowed to play either 0 or 1 at every round. Player one has to play so that if player two has played I alpha in one round, then the next move of player one has to extend I alpha. So the next move has to be a sequence of the form whose first element is I alpha. So that's what's going on in this game. And at the end of the game, they construct an element of the Baire space, of the kappa Baire space. So you take the concatenation of all these TIs that player one has played. So you concatenate, you get an element of the kappa Baire space, and you check whether it's in the set X or not. So if it's in the set X and player one could obey this rule, then he wins and player two wins otherwise. So in the omega case, this is a classical game characterizing the perfect set property, and Kovachev showed that in the kappa case, in the uncountable case, it also characterizes the kappa perfect set property. So player one wins. So when I say that player one wins a game, I mean that he has a winning strategy. So player one has a winning strategy in this game, if and only if there's a continuous injection from 2 to the kappa into X. So a continuous injection from 2 to the kappa into X corresponds to the existence of a kappa perfect tree. So like some subset of functions from 2 to less than kappa with some nice properties. And such a tree corresponds to the existence of a winning strategy. And player two wins if and only if the set has size as most kappa. So let's look at the direction from right to left for player two. Let's suppose player two has a winning strategy. Suppose X has size less than or equal to kappa. Enumerate X in a sequence of length kappa. So let small x alpha denote the alpha element of X. And in round alpha, the strategy of player two is to make sure that the alpha element of X, so X alpha, is avoided in round alpha. So since there are always two options for I alpha, player two can choose in such a way that all the elements of X alpha, so the X constructed at the end of the round can be equal to X alpha. Just make sure that the alpha coordinate is different. So in particular, the perfect set property is equivalent to the determinacy of these games. So in the classical case, so for Polish spaces, Alexander Kepris introduced a general class of games of countable length, which encompasses many of the classical games characterizing dichotomies for subsets of the Baire space. And we consider the version of these games of uncountable length. And we're going to try to prove the determinacy for for a broad class of definable sets. So Caprice's games, in some sense, generalize the game for the perfect set property. So in round alpha of the game, player 2 in the perfect set game, he played either I alpha equals 0 or I alpha equals 1. And this was a requirement for player 1 to extend I alpha in the next move. In this more general games, there's a set of non-empty set of requirements R, and there's a function f from R into the power set of equivalence and kappa. So the power set of possible moves for player 1, which tells you, so for small r in this requirement set R, f of small r tells you which are the next legal moves of player 1. So this is a similar game to the previous game, except instead of T alpha plus 1 has to extend I alpha, I have to make sure that T alpha plus 1 satisfies this requirement R alpha, and this function f tells me what exactly I mean by satisfying a requirement. So in each move T alpha plus 1, I have to make sure that T alpha plus 1 hits this set f R alpha. And again, I get a sequence by concatenating these T alphas, and I have to make sure, or player 1 has to make sure that it's in X. It's in the winning set of winning conditions X. So this is the general form of the game. And so for example, the kappa perfect set property is equivalent to this game for the requirements set R equals 2, so 0, 1. And the ith requirement F satisfies requirement I if and only if the next move, so T extends I. Okay, so there's these two assumptions on R and F, which I'm not going to describe. It's just for technical reasons to make sure that this set of requirements and this function F are non-trivial and give us something interesting. So another example of another regularity property which can be characterized with using such games is the Hurewicz dichotomy. So here you see again the definition of the game. And let's look at a specific example where the requirement set is kappa. And for a requirement R, I have to make sure that T0, so the first coordinate in T is at least R. And if kappa is weakly compact, weak compactness is just another large cardinal property. So if kappa has this large cardinal property, then player 1 winning is equivalent to there being a closed homeomorphic copy of the kappa graph space in X. So player 1 has a winning strategy in this game if and only if X contains a closed homeomorphic copy of the kappa graph space. And player 2 wins if and only if X is contained in a union of kappa many kappa compact sets. So kappa compactness is just a generalization of compactness where finiteness is replaced by less than kappa. So every open cover has a subcover of size less than kappa. And so I get a regularity property which characterizes compactness in some sense, or kappa compactness in the generalized case. For non-weakly compact cardinals, I get a more technical generalization of the Hurewicz dichotomy and of compactness, which I'm not going to describe in this talk. And the third regularity property, which I'm going to skip, is a generalization of the kappa Baire property. So, if you look at the Baire property, it's equivalent to a game of length omega. And if you extend this game to length kappa, you get a regularity property that makes sense. And this game can be is equivalent to a game of the form of Caprice's games. So what was known for definable subsets of kappa to kappa before? So by a definable set, I mean a set which is definable using a first order formula with one parameter, which is a sequence of ordinals of length kappa. And for example, kappa Borel, kappa analytic, and kappa projective sets are all definable. So you can just think of kappa projective sets. It was known before that the kappa perfect sets property, the asymmetric kappa Baire property, and the Hurwitz dichotomy, so the three things I mentioned on the previous slides, are all consistent for definable subsets of kappa relative to an inaccessible cardinal. So it makes sense to hope that this general class of gains, or the determinacy of them, is also consistent relative to an inaccessible or to maybe some large cardinal property. And we proved that this is indeed the case. We proved a more general dichotomy theorem for infinite dimensional open hypergraphs, which I'm going to tell you in a second what I mean by that, which implies the determinacy of this general class of gains. So you recall that the perfect set property says that either X has size at most kappa, or there is a continuous injection of the kappa Cantor space into X, and a version of it for open graphs. So by a graph, I just mean a symmetric and irreflexive subset of X times X. And by an open graph, I mean that it's an open subset of the product space. So a version of this perfect set property for graphs, the open graph dichotomy, says that for any open graph G on X, either G admits a kappa coloring. So that means that X can be written as a union of kappa many sets which are G independent in the sense that they contain no edges of G, or there is a continuous homomorphism from the kappa Cantor space into X. So by a homomorphism from the complete graph, the complete graph on the kappa Cantor space to G, I mean a map such that for all different elements in the kappa Cantor space, they get mapped to an edge of G. So it's just a copy of the complete graph onto the kappa in G. And note that any such map F is injective. So this OGD implies the perfect set property if you take the special case of the complete graph on X. And what we were looking at is an infinite dimensional generalization of this dichotomy for infinite dimensional directed hypergraphs. So Kara, Miller, and Soucoup introduced such a generalization for the case of Polish spaces, and we looked at the version for generalized Baire spaces. So by a directed hypergraph with dimension D, I just mean a set of non-constant sequences in X to D. So the fact that it's directed just corresponds to the fact that I can take any sequences and there is nothing corresponding to be symmetric. And I'm going to look at the box topology on the set of sequences in X of length D. And I'm going to call a hypergraph open if it's open in this box topology. So the box topology is basically the broadest topology you can imagine on this product space, where you take products of open sets UI for each I and D, and I can choose any open set here. And I'm going to skip the definition of this dichotomy, but it says basically that for all box open dihypergraphs H on X, either it has a kappa coloring, or there is a continuous homomorphism from some large canonical hypergraph to H. And by a kappa coloring, I just mean that it's a union of H independent sets X alpha. And by a homomorphism, I mean that hypergraphs get mapped to hyper edges. And this canonical graph H that I have on the top of the slide is in some sense the generalization of the complete graph onto the kappa, but not the most trivial one. No, so it's not the complete graph, not the complete dimensional graph. It's just some other way of generalizing it. So ODD says that this holds for all box open dihypergraphs H on X, and there is also a version for hypergraphs which are definable in some sense. And we showed that the version for hypergraphs which are definable is consistent relative to an inaccessible, and the full version is consistent relative to a Malo cardinal, where Malo is just a slightly stronger large cardinal property than inaccessible. But right now I care about the fact that if I look at the version for definable hypergraphs and definable sets, so definable in the sense that it's definable from a first order formula with a kappa sequence of ordinals as a parameter, or specifically for kappa projective versions. So this is going to be this is consistent relative to an inaccessible, and the result is that this definable version implies the determinacy of Caprice's gains for length kappa, assuming that these assumptions, technical assumptions, are satisfied, and hence this determinacy result is consistent relative to an inaccessible cardinal lambda greater than kappa. And this gives a new proof for the fact that the open hypergraph dichotomy implies the three regularity properties that I had on the previous slide. So in particular, Wurlitz dichotomy, the kappa-Baire property, the asymmetric kappa-Baire property, and the kappa perfect set property, although the third one is kind of trivial. And the proof goes by basically choosing the hypergraph HF that you want to work with in a clever way, and showing that if you choose HF in this clever way, that one wins the game if one having a winning strategy corresponds to the existence of a continuous homomorphism, and two winning corresponds to the existence of a kappa coloring. And basically what I'm doing is I'm taking the hypergraph defined by the requirement sets R and their function f from R to kappa plus and kappa. So I'm taking some hypergraph given by these requirements in a natural way. And I think my time is up, so I'm not going to go into the details. And thank you for listening.